So welcome. Today is assignment 2 day for Computer Science 4303. So have a few more viewers than normal at this time. People always want to know what the assignment is about. If you're watching this on YouTube and you're not in the class, I apologize, but the assignment files will not be released to the public. The assignments take a long time to make, and as soon as they go to the public, then there are solution codes everywhere, and so I really don't want that to happen. So as you see, today is assignment 2, and you will have 2 weeks and 2 days, so 16 days to complete assignment 2. I think assignment 2 is actually going to be really fun. At least I had a lot of fun making it, and I added some new bonus features to this one, so I hope you enjoy writing this assignment. Okay, but first, before I get right into the assignment, I'm going to do a little bit of a recap of what I did last time. So let's switch over here to my PowerPoint of Path of Exile. We looked a little bit at Path of Exile last time and some motivation for what we're going to be doing in assignment 2. And I just want to show you that again. So here in Path of Exile, I'm not going to explain everything, but I did want to show the type of pathfinding that we're trying to look for in this assignment. So here we go. So I'm in Path of Exile. I can move around. I'm about to go to an area with a lot of enemies, and I want to show you the pathfinding that we want to do for this course, or for this assignment at least. So this is called a map in Path of Exile. I'm not going to explain the mapping system, but it's essentially an area that's going to have a lot of enemies. So you can see here that already I've run into about 150 enemies, and they're all pathfinding toward me. Right? So every enemy on the screen wants to get to me and kill me. And so you can see here that that there's a many agents to single goal type of pathfinding going on here. And there are a lot of them. And we want to have a system that will allow us to do really efficient pathfinding for lots of enemies to a single point. We don't want to have to run a pathfinding algorithm for each one of these enemies individually to get to me. Okay. Someone asked, what game is this? This is called Path of Exile. And just let me show you, I'll spawn a whole bunch more enemies that will come toward me. So here we go. Things continuously spawn and continuously come to me. And we want a very fast, very efficient pathfinding algorithm that can deal with that sort of situation. Someone in the chat asked, which game is it? This is Path of Exile. It's a top-down 2D action-adventure RPG, or action RPG, I guess you could call it, very similar to Diablo. Someone else asked, did you run Assignment 1 competition yet? Assignment 1 isn't due yet, so no, I haven't run the competition yet. So that's what we're after, and that's just sort of the motivation going forward for this assignment. So let me exit out of here, and we'll get into the assignment proper. Okay, so here we go. So I've got the assignment open here in Visual Studio, and as before, I will go through all the code, but what I want to do for the assignment first is just go through the solution and show you what the assignment is about. And then we'll go through the text file that will explicitly tell us what we have to do for the assignment. And then I'll go through the code to show you where you need to edit things and what sorts of things you need to do and exactly how the assignment works. So let's load up the solution here. Okay, so that should be full screen. Perfect, it works. Let me make my camera a little bit smaller. So this is the environment for assignment 2, okay? And we said before that we're going to be doing essentially a grid-based navigation mesh and a vector field pathfinding system. Okay? So what we see here when we open up the assignment is a bunch of rectangles. These are all defined in an environment file. And we see this yellow spot here that I'm dragging around with the mouse. That is going to be the goal or the destination for the pathfinding, okay? And our goal here is to create a vector field that can pathfind from anywhere in the map to the destination, which is this yellow point here. So I can drag around these rectangles if I want, and as you can see here, what's happening is that some parts of the map are turning red and some parts aren't. So what this means is that the black area of the map, that's the blank area. That's where my NPCs and my characters should be able to run around, okay? So that's the navigatable part of the map. The red part is the part of the navigation mesh that I can't walk on, okay? So for example here, these rectangles, you consider them as obstacles in the environment. And when I drag these around, you can see that any cell, actually let me make the environment a little more coarse here. Any cell in the navigation mesh that any rectangle is overlapping with becomes blocked, okay? So we can see here, as I drag around, some parts are becoming black, some parts are becoming red. So that's kind of the first part of the assignment, is that as you drag around these rectangles, you're going to have to be updating this navigation mesh in the background, which is just marking these cells as walkable or not walkable. Someone asked about light red versus dark red in the chat. There is actually no difference. It's all just red. It's just that these rectangles are semi-transparent and make it look a different shade of red, okay? So these are, anything that's red whatsoever is unwalkable. So you can't walk on that area. So let me just make this the default size again. So what we're going to do is, oh, and I can also like add rectangles to this with certain keys. And I can move around things. So it's a little bit finicky, but I did program it in, and all this is done from scratch. All of this mouse dragging and resizing is all coded by me. So if you want to resize a rectangle, you have to click sort of right inside the edge within like 15 or 10 pixels or something like that, and then you can drag it, okay? And so you can drag all these things around, and that's how you sort of edit the environment. Now, there is a help screen. So if I press H, the help screen will come up. This is the solution. So for the solution, there's some extra fun stuff, which I'll get to down here. But these are the controls to the environment. So I can add a new rectangle. I can increase or decrease the number of grid cells. It just doubles them or halves them. I can toggle the vector field display, toggle the navigation mesh display, or toggle the grid line display. So what does that mean? Well, toggling the grid lines, that's pretty intuitive. If I press the G key, it draws the grid so you can see exactly where all the cells are. If I press the D key, then that will toggle whether or not we're actually drawing the underlying navigation mesh. Okay, so if I press D, it'll draw the navigation mesh or not. And you can see that these are just gray rectangles that when the red background is shown, it looks like a dark gray, but there's no difference between the interior of the rectangle and these red cells. What was the other key? Oh yeah, so the other key, which is the A key, is really important. What that's going to do is that's going to toggle between the distance map or the vector field display. So if I hit the A key, what we see is the computed distance map for the current destination that I have selected, okay? So you're going to be computing this using a breadth first search, and we did that in the last lecture, or showed how to do that. So you can see here, let me just increase this a little bit. So whenever you resize the map, you just have to click again for it to register. And you can see here that at the destination, it's a little bit hard, but there is a 0, meaning that this cell is 0 away from the destination. As I move further and further, the breadth first search is going to increase the distance by 1, where we can see, like, you know, this tile up here is 16 distance away from the goal. So if I go back here and click again, then we can see that as I drag around, like, this is updating in real time, right? Okay, so this is the distance map calculation. If I hit the A key again, remember how we got from a distance map to a vector field? Well, all we did was we point for every cell, we draw a vector to each of the lowest valued cells around it. So if I hit the A key, what I'm now drawing is the vector map. All right, and remember, this is the solution. This is not done for you. This is what you're going to have to be computing. So as I drag this thing around, it is updating the vector map in real time. And every time I drag this yellow goal destination cell to a new cell, it is recomputing the vector field. Even when it's not being displayed, it's being recomputed, okay? So down here, what we see is some timing code, and pretty much the resolution of this timing code is around 60 microseconds or 70 microseconds. So this is it's only 1,000 cells. So my solution code, which is very, very heavily optimized, is being computed like within 60 microseconds. It's actually taking longer to draw this scene than it is to compute the underlying vector field. However, as I increase the amount of cells, you can see that the timer for computing the vector field goes up and up. So here, now I have approximately like 58,000 cells. You can see all those grid cells on the map. So it's much finer detail, but it is still only taking about 2.5 milliseconds. So 1,000 microseconds is a millisecond. And so it is still only taking about 2.5 milliseconds to update this really, really big map. So I don't expect your first iteration of this is going to be quite as fast, but I do challenge you to try and get to my time, okay? And we will have a little, the top 3 finishers I'm going to show in the next class as sort of, bragging rights that you made the top 3. So one of the things I wanted to show you here is that this is one of the downsides of using a grid, is that, for example, right now, we're using this grid for a navigation mesh, and we can see that even though we're only moving this rectangle by like 1 pixel, the resolution of the grid really matters for the underlying pathfinding. So for example here, if I have this rectangle like almost to this grid cell, and this rectangle almost to this grid cell, there's a very wide path here that you can take. But just by moving this over by like 2 pixels and this one over by 2 pixels, now even though, yes, technically there is space between these rectangles, our underlying grid representation just got really unlucky on those borders, and now there's no way to get through here, okay? So if we look, and if I show you the distance, the vector, actually the distance map is probably better to show here. This tile right here is 43 distance away from the goal. But if I move this over just by like 2 pixels, then it's only 15 away from the goal, okay? So one of the ways that we can try and solve this is to like position our rectangles really carefully so that they align with the grid properly. Or what we can do is just increase the resolution of our grid, right? And then that will help us solve that problem. But of course, we just have that problem at a different scale. So then maybe we go up again and we keep increasing the resolution, but we use more memory and we use more time, okay? So that's one of the trade-offs that you have with grid-based navigation meshes. Okay, so now I want to show one of the bonuses that I sort of did for this. So if you do all of this stuff, so here you have the computing of the navigation mesh, just a marking of the cells as a 0 or a 1 with the rectangles in the environment. Then you have the distance map, which you calculate using a breadth first search. And then you have a vector field, which you calculate using the distance map. All of that, if you do it correctly, will get you 90% on this assignment, okay? To get the extra 10%, or not the extra, but the last 10%, you have to make a little bit more effort. And what we're going to do is that you have to add some particles somehow to the map that actually pathfind along the grid. So I want those particles to like spawn in random locations and then actually pathfind to this goal location. So I've done that. And we can see down here, there's like a particle count and a particle timer and stuff like that. What does that mean? Well, I'm going to press the P key in the solution to turn on the particles. So here is the particle system that I made for this, which follows the vector field toward the goal. So this particle system uses the vector field for pathfinding. And what I've done here is that I've just said, okay, I'm going to spawn 1,000 particles. They will pathfind toward the goal. And once they reach the goal, so once they overlap with this cell, they actually respawn at a random location on the map. And another thing that I've done is I said that if a particle ever spawns within a rectangle, it just respawns randomly. And if a particle goes off the edge of the map, where there's no vector field to guide it, of course, then I'll respawn it, okay? Now, the really cool thing is that you may say, like, oh, like, how fast is this? Well, we're currently getting between 1,000 and 1,200 frames per second of performance with a grid of 1,000 cells and 1,000 particle count. Okay. I see that there are some questions in the chat. I will go back to those afterwards. I just want to explain the assignment first. So you might say, okay, say in the chat how many particles you think my system can handle until it goes below 30 frames per second. How many particles do you guess out there in the chat that this system can handle? So right now, 1,000 particles is taking 300 microseconds to compute. So I've got 15,000. Someone has a lot of confidence and said 150,000. All right. So if I look at the help screen, that's a cool effect, hey? Just blurs the background. So I can toggle the particle display with the P key. I can half or double the number of particles with Z or X, and I can half or double the particle size with C or V. So what particle size is just literally a display option, right? So I can make the particles really big if I want, or I can make the particles really small if I want. And actually it looks, you can't really appreciate this on the stream, but this starts to look really cool when you're actually watching it in person. All right, so let's go back to the default particle size. I think that's what it was there. Okay, so the Z key is going to decrease the amount of particles, and of course, you know, that's really easy to do 32 particles, but every time I hit it, it's doubling. So here we are, we're back at 1,000 particles, or 1,024. Here we are, 2,048, 4,096, 8,100, or 8,200, 16,000, 32,000 particles. Okay, we're still at 200 frames per second. 65,000 particles. We are still at about 100 frames per second. Right? And I can edit all this in real time, and it's all doing the dynamic updates. See, just look. This is really cool. So as I drag this, you can really see the effects of the size of the grid now. Right? Oh, I should add that there should be like a seizure warning for this, because if I'm about to, yeah, I can probably understand that my cam is going blurry and everything's going blurry because of the compression on this. So you're really not going to be able to appreciate this unless you run it in person. But I can see all 60,000 particles like very, very clearly. But watch this. You see this? Okay. Okay. So we're still at. So I've got 262,000 particles running at about 30 frames per second. All right. So I know that this is terrible for the compression and for Twitch, but I'm going to put it back down. But 262,000 particles, that's kind of crazy, right? And that just shows you how powerful this pathfinding can be. So let me put this back down. All right. So hopefully I've got a webcam back now. All right. So I just showed you like how fast this can be if you optimize it, right? Like this is pretty cool. So let's just show you that in real time, as I'm updating, like you can see that these particles that spawn up here have a path down. But now if I move this rectangle, right, there's still blank space, but the reason they have to go around is because the underlying structure doesn't have that, right? You can see the particles going through here now, but now they can't, right? All right. So, oh, sorry. Whenever you increase or decrease the size of the grid, you have to just press the button again. So this is cool. I like this. I spent way too much time on this. Yeah, someone mentioned that if you put that simulation on the GPU, you could get a lot faster. So someone asked about what's the bottleneck here. So I've got all the timers down here. So let's just have a look at the bottleneck. I know it's kind of difficult to read, but when I get up to 131,000 particles, it's the particle position updating that is the bottleneck, okay? So the particle position updating is the bottleneck. The drawing of 200,000 particles takes 4 milliseconds. Okay, that's all done in a vertex array, so that's really, really quick. Okay. So, someone else asked, are the particles independent or do they collide? The particles collide in my system with the rectangles. So they collide with the underlying grid, but they do not collide with each other. If I had particle-to-particle collisions, this would be much slower, of course. What other questions do I have? All right. So yeah, I spent a lot of time optimizing this. So I did that in order to show you just how fast this can be if you put time into it. And this is, the sort of thing you would want to do if you're actually making a retail game engine. Okay, someone said it looks like the particles are clipping the rectangles. So the collision with the rectangles are done with the center point of each of the particles. Okay, so that's why it looks like it's clipping a little bit. It's just because they can overlap by half of the particle, and that just makes it a little bit faster. Now, so for the extra, so to go from 90% to 100% on this assignment, you do not have to do this sort of level of optimization, right? You can just have even 1 or 2 things that spawn on the map, right? Like if you have something like this, oh geez, like 1 or 2 things that spawn on the map and go toward the goal. And you can even see here that my system, when the particles get really big, there is a little bit of a bug here where they sort of get stuck, right? So this would get you full marks. And you can get up to 5% bonus marks by actually doing some steering behaviors as well. So if you just implement this naively, your movement will look really rigid, and that's fine. That will get you full marks. But you can get up to 5% bonus marks by doing a steering behavior. And what steering behavior is, you can really see a steering behavior. If I increase the number of particles, hopefully the rendering doesn't, or the encoding doesn't ruin this, but you can see that as the particles are moving like around the corners of objects, they do have this sort of flow to them, right? And that's because what I've done is I've given every particle a randomized steering force, and that steering force is like how smooth their turning is, okay? So the steering force sort of simulates inertia, but there's no mass or force or anything in this simulation. Neither do you have to do one. Someone out there said, can you please explain the basics of the pathfinding algorithm? If you type !playlist, you'll see the playlist of lectures for the course, and it's all there, so I'm not going over that again. And someone said, are they getting stuck because there are 2 paths of the same value? No, they're getting stuck because I didn't spend enough time on my algorithm to unstick them. It's good enough, right? It's good enough for a class assignment. If I was making a game, I would optimize, or I would spend a lot of time programming to get those things unstuck. Okay, so that's the assignment. That's the solution code. But what you are given is this. Okay, so this is what you get when you get the assignment. So you get the same environment. However, what you get is no underlying vector field being computed or no underlying grid being computed. You just get this. You see one square here has sort of been hard-coded to be blocked even though it's not true. If I hit the A key, all of the distances are given a value of -1, which is obviously not correct. If I hit it again, then none of the vector field positions have values except one of them, which has been hard-coded to say move to the right and move down. And of course, this is all incorrect, and you have to modify your assignment to actually work with this, okay? So if I make it a little bit bigger, you can see this a little bit. So just as an example in the code, I've given you how to set these values and how to modify the values, etc. But none of this is actually working properly in the assignment. So if we look here, nothing is happening. But if I were to go back over to the solution and do the same thing, then this is what you would expect to see, okay? And as you drag this around, the vector fields are being updated. And if you turn on the particles are working. Perfect. Okay, so that's how the assignment looks, and that's the point of the assignment, right? We looked at Path of Exile and we said, okay, how could we do really, really fast multiple enemies to a single goal? Well, our system doesn't have a lot of the collisions that Path of Exile does or things like that, but without interparticle collisions, this is able to do, 200,000 or so particles at a time, which is pretty neat. Okay, so now we'll look at the text file that explains the assignment, and I will show you, and I want to read through this just to make sure that I have actually explained it correctly in the text file. Okay, so submission. For this assignment, you will zip and submit the entire source folder for the assignment. So in the last assignment, you only submitted one file. This time, you're going to right-click on the source directory and zip that. Okay, so everything in the source directory, you are going to submit. You are not allowed to add any files in addition to the ones already in the source folder in the assignment zip file. So that means that you can't make any changes to the Visual Studio project. You're just submitting the source folder zipped up with no additional files. If you want to make an additional class or something like that, you can totally do that. Just make it inside one of the files that I've given to you. So this means that you will not be submitting any changes that you have made to the Visual Studio project if you use it for development. So do not add any additional files, okay? And the reason I'm being strict about this is because it takes a long time to mark these assignments. And so what we're doing essentially is we have one Visual Studio project set up, and all we do to mark your assignment is we drag in your source folder and replace the current source folder. And we open up the Visual Studio project, all the new files are imported, and then we can run your assignment. So that's why we do that. So any additional functions or methods must be included in the original files distributed with the assignment. You must include the following info at the comment at the top of main.cpp, so all of your names in the group, so both of you or just one of you if you're single. And if you didn't get a specific feature to work, please explain what you tried to get working, and we could give you partial marks for that. Okay, so that's all standard. Here's the program specification for this assignment. So in this assignment, you will be computing 3 different grids based on an environment which will be specified in a configuration file, and I'll give the details of the configuration file a bit later. So the 3 grids you must compute are located in the vector field class as a member variable, and are to be computed whenever the vector field compute function is called. They are as follows and must be computed in this order. So over here in the Visual Studio project, I'm just going to open up the vector field class. So the vector field class is going to have a number of variables in it, and it's your job to write the compute function for the vector field class. Okay, so that will get you 90% of the marks on the assignment. So the vector field has some unsigned integers here. It has the spacing, that's the spacing of the grid in pixels. It has the width and the height, that's the number of rows and columns in the grid. And it also stores the goal X and the goal Y position. And then here are the 3 grids themselves. There's a grid of integers. That is the underlying grid of this space is either blocked or it's not blocked. Then we have another grid of integers, which is the distance map. And then we have a grid of vectors of directions, which are the vector field. So every spot in the grid can have 1 or more directions, or actually 0 or more directions that you can head in to get to the goal. And so by default, this might not be the fastest solution that you end up using, but by default, this is stored as a grid of vectors of directions. And directions are just objects which have an X and a Y component, okay? So you can go up, down, left, or right, whatever. Okay, so let's go back to the file here. So those 3 grids are what you have to compute, and that makes up 90% of the assignment. So the first grid is the blocked or unblocked grid, and that is just the m_grid variable. So this grid is used to denote whether a grid cell is considered blocked or unblocked by the rectangles in the environment. A blocked cell is denoted by a 1, an unblocked cell is noted by a 0. If any rectangle in the environment intersects with any part of a cell, it should be considered blocked. You can access rectangles in the environment by calling the function environment getRectangles. which returns a vector of rect class objects which are defined in rect.hpp. This grid must be computed first in order to compute the next grid. So here's something that I, as someone who have a lot of programming experience now, take for granted, is that what I still find students saying in computer science, even at the 3rd and 4th year levels, is the way they approach an assignment or a program is that they'll open up the assignment, they'll write all of the code, and then they'll try and run it. And that is not the way you should be writing software at a senior undergrad level, okay? I tried to go over this a bit in 3200, but what you want to do is write a little bit of code, test to see if it works, and once you're sure that that part works, you go on to the next part, right? You don't build a whole house at once without first testing the foundation and then testing the walls and then testing the roof and then, you have to build up little by little. So what you should do is not write all of the code for 1 and then write all of the code for 2 and then write all of the code for 3, is you should write all of the code and then make sure your blocked or unblocked grid is working first, okay? So we're not going into things like testing, like unit testing or anything like that in this course, but what you do have to do is go one step at a time, okay? Make sure this is working before you go on to step number 2. Because I have literally seen students write an entire assignment, 300 to 400 lines of code, and then not know why it's not working, and they haven't tested anything along the way. So just make sure that you're doing this in a sort of iterated method where you do one thing, make sure that works, and then go on to the second thing. That's how you'll be writing software for the rest of your life if you end up being a software developer. Okay, after you've computed the blocked or unblocked grid, first of all, I wanted to show this rect.hpp. So rect is just a very simple rectangle structure. It contains an x, a y, a width, and a height. So the x is the position of the top left corner x coordinate, the y is the top left corner's y coordinate, the width is the width of the rectangle, and the height is the height of the rectangle. These are measured in pixel coordinates, not in cell coordinates, okay? So I've just created this very, very simple rectangle class, which has an equals operator. It has a contains a point operator or function. And I've just shown you here, excuse me, that if you want to, you can add more functions to this rectangle class if you want to. That might help you with the assignment. I don't know. But that's where it is. It's in .hpp. So so far in the class, I have only explained .h and .cpp, right? .h would be the header file, .cpp would be the implementation or CPP file or C++ file. If you see .hpp, that's called a header-only file where both the header and the implementation are done in the same file. Sometimes you do this if you're writing library-type stuff like a rectangle class, and so here, this is a very simple class that I did not want to have to split into 2 classes, a header and a CPP file, so I just left it as .hpp. And you can also see that this timer class that I did, it's really simple, so I just left that in an HPP. But again, the file extension doesn't really matter, it's what's in the file that matters, right? But that's just a convention, is to use HPP where you have everything in the header file. Okay, step 2 is computing the distance map grid. And this will be the m_distance grid inside the vector field class. So this grid is used to compute and store the distances from all cells to a given goal cell. The goal cell is gx, gy in the compute function parameters. The distance map is to be computed using 4-directional cardinal movement with each action given a cost or distance of 1. It is not mandatory that you compute the distance map with a BFS, but it is probably the easiest and fastest way to do so. The distance map should be given initial values of -1, which denote that no path exists to the goal from a given cell. This grid must be computed in order to compute the next grid. So let me just show you something real quick with the solution, okay? So if I have the goal down here, and I have the distance grid pulled up, let's see what happens if I actually create a section of the environment which is not reachable, okay? So these cells up here cannot reach the goal, all right? So any cell that cannot reach the goal, so did not get reached by the BFS, remains -1. So what you do is you start out with a grid of integers that are all -1. You do a breadth first search out from the goal, increasing the number with the algorithm that we said last time, and this is how you get your distance map. But your distance map is going to be -1 for everything there. People asked, what about particles? Right now in my particle system, what happens is if I ever spawn on a location that has a -1, I respawn at another random location, okay? So you could do the same thing in your particle system if you want. That stuff really doesn't matter. That is completely up to the designer of this game. But yes, if there is no number, if there's no distance, then there's also no vector field, so they wouldn't know where to go. So they would either get trapped there forever, or you could respawn them, or you can do whatever you want. It doesn't really matter. Okay, so the last grid is the vector field or direction grid, and this is the M directions grid. That's the name of the variable inside the vector field class. Each cell of this grid stores a vector of direction objects, each of which consists of an X and Y component. The directions stored in each cell must point to the adjacent cell with the lowest value from the distance map. If there is a tie, then all directions pointing to all lowest values must be stored in a cell. Okay? So that means if you could go up or left, then you should have an up or a left. And again, let me just put... I'm going to put this in here now because I forgot. So the legal directions are... we're going to make an array here, and this is going to be 0 or 1, 0. That is right. Then we're going to have -1, 0. That is left. Then we're going to have 0, 1, which is down, and we're going to have 0, -1, which is up. Okay, so let me just put this in here. So this is right. This is left. This is down, and this is up. So in that grid, the M directions grid, you're going to have a vector of direction objects. And again, directions, if you look at vectorfield.h, just have, let me change this to an int for you. Moving this to a char was one of my little optimizations, but that's fine. So you have an X and a Y. They could be any arbitrary value, but for this assignment, the only legal values that they can have are up, down, left, or right. Someone in the chat asked why -1 in the Y direction is up, and that's because in SFML, which is the graphics library we're using, 0, 0 is the top left corner, and at Y decreases going downward. Okay, and the last part, moving entities, that you saw, I did this as a particle system. You could do whatever you want for this. 10% of the assignment grade is reserved for adding some sort of moving entities into the GUI, which follow the directions of the computed vector field. Getting this to work with 100 particles or more will ensure that you get, let me do 10. Okay, with 10 particles or more will ensure that you get the full final 10% of the grade. Important note, you must calculate each grid each time compute is called. I realize that if the environment rectangles do not change, then the blocked grid does not need to be recomputed. But please recompute all 3 grids all of the time. This way it will be possible to fairly time all of the solutions of all students. So what do I mean by that? Okay, so for example, if we had the assignment running, right here, I want you to, every time I call compute, you have to recompute the entire thing from scratch, okay? Even, so if you were making an actual retail game, what you would do is that when I call compute, you would check to see, hey, have any of the rectangles moved? If none of the rectangles have moved, then I don't need to recompute anything, right? If my underlying grid stays the same, then I do not need to recompute. But however, in this assignment, I do want you to do that, okay? Oh, and I forgot to mention, sorry about this, one of the important parts is that if I press, so when I run the assignment, you get the GUI here, but you also get, crap, Okay, 1 second. Yeah, okay, so I turned off the full screen. You get the user interface, which I'm currently dragging around, but you also get the terminal, right? If you press the T key, okay, on the keyboard, what will happen is as follows. Okay, so you can see here that I've got a fairly large grid, and if I press the T key, what it does is it runs a timing test, and I know this is a little bit small, but it computes the vector field so it loops over every cell in your grid, sets that as the goal, and recomputes the vector field for there. So it's a really good timing test because it does it for every possible location in the map. So here in my code, let me see if I can make this a little bit bigger. Okay. So for my solution code, for this sized grid, it did 2,565 vector maps. It had an average of about 60 microseconds per vector map, and the total time was 0.146 seconds for that, okay? So when I talk about the fastest 3 assignments in the class, we are going to press the T key for every assignment in the class, and the top 3 will get a little bit of a, not bonus marks, but they will get mention in the class, and I'll run their assignments in the class. So that's what we're using to time things, is this, by pressing the T key from inside the program. Okay, so let me go back here. Here we go. So you must also calculate and store the results of all grids. You are not allowed to be sneaky and calculate individual cell results when the get direction or get distance functions are called. You must compute the values of all grid cells once in the grid function. The get grid, get distance, and get direction functions must only return pre-calculated values stored somewhere in the vector field class. So that just means these two things just mean there's no sneaky shortcuts to get around computing the whole vector field. All right, we want you to compute the whole vector field, but if you were making like a retail game and you wanted it to be as fast as possible, you would include some of these optimizations of checking to see what it is you actually had to compute and then computing them only if you need to. But in this class, we are computing everything. So the GUI description and goals, the user interface has been implemented for you. It draws all of the rectangles of the environment, as well as the grid cells and values. Unblocked grid cells are shown as empty, while blocked grid cells are shown in red. A timer is drawn to the bottom left corner of the screen, which displays how long the previous call to vector field compute took. And this is measured in microseconds. Mouse controls, you can set a new goal position with the left mouse button. The mouse can be dragged around while the button is held to continuously recompute. You can click and drag the center of a rectangle to reposition it. You can drag the sides of a rectangle to resize it. So if I just open up the solution again, something I want to show is that as I'm dragging around the goal location, it will only call the compute function when I move to a new cell, okay? So if I'm dragging the goal around within the same cell and the cell isn't changing, the compute function is not being called. But if I change it to another cell, then it is being called, okay? So that's what that's doing. And you can see this down here. The field timer isn't changing unless I go to new cells. If I press T, it'll run the timing in the background. The keyboard controls, I don't need to go over that because it's all there for you. And if you press the H key, it'll bring up the in-game control menu. Okay, the configuration file, this is pretty simple. Here's the config file. It just has the width and the height of the environment, and then on each line, it'll specify a bunch of rectangles, okay? But that's done for you anyway. It's just there. We will have like a secret config file that we're going to test the assignment with, but it's just here in case you want to modify it to test your stuff, okay? This shows you the exact specification, but it's so simple I don't need to explain that. Extra incentive and bonus marks. So the top 3 fastest running code will be run live in class. I will also talk to the groups about what they did to optimize their code. You will also receive a little D2L trophy, which I will give to you for that. You can get up to 5% bonus marks on the assignment by implementing steering behaviors for the entities that move around the grid. And I've already talked about that. Here's a couple of assignments hints. You are allowed to change the grid.hpp class to try and make it faster. Just be sure not to change any existing function declaration syntax so that the class will still work with the user interface. What do I mean by that? Well, if I go over to the grid, this is the grid class that we talked about in class before, okay? So it's all implemented here in the HPP file, so there's no header and implementation, it's just the one file. So the grid stores, it's a grid, which is essentially a 2D array, and the way that I have implemented this is that I am storing a vector of the given type. Okay. Now, the reason I mentioned that you might want to modify this is that it's possible that this is not the fastest possible way to implement a 2D grid in C++. Okay, so you are completely allowed to change the underlying two-dimensional grid. For example, maybe you want to represent a 2D grid as a one-dimensional vector structure and then do the math for the index calculations. You can completely do that if you want to. However, none of these function syntaxes can change. All right? You have to not change these things. There you go. Okay. Because this is what the GUI uses in order to operate. So you can't change, like, if you change the underlying structure of the grid, you still have to have this function unmodified. And you'll very quickly see that if you modify those, everything will break. So that should be pretty obvious. You can change the way that the grid data is stored in the vector field class from the way that it is given in the example. However, I recommend first getting it to work properly with the example grid code, since that is by far the easiest way of getting the assignment to work properly. So what do I mean by that? Well, as we showed in the last lecture where I talked about the optimizations at the end of the last lecture, maybe storing a grid of vectors of directions is not the best way to compute the vector field. So you can change the underlying way that these things are stored as long as these functions still operate properly, right? So, for example, the way that the user interface grabs data from your vector field is through the getGrid value, which takes in an x and a y. The way that it gets the distance is the getDistance value. The way that it gets the directions is the getNumDirections and getDirection functions. So these functions, this uses data encapsulation, right? The GUI doesn't need to know or care how you're actually storing these grids. You just need to be able to get access to the data via these functions. So you can change the way that this is stored if you find that it works faster. Okay. So now what we're going to do is we are going to go through the code really quick to show you how it all works and to show what you need to do for the assignment. So the first thing I'll show is just what you need to do for the assignment, and then after that I'll go through how the user interface works, etc. So first, let's show what the environment is. So the environment is very, very simple. It's going to store a width and a height. These are stored in pixels. That is the width and the height of the actual environment, like the in-game pixels, not in cells, because the environment doesn't need to know anything about the vector field or the navigation mesh. And then it just has a vector of rectangles, okay? And so you can get access to the width or the height of the environment with these functions, and you can get access to the rectangles to add or remove rectangles or get the properties of the rectangles like that. So you will need to access the rectangles in order to compute your grid. So that's why I'm showing you the environment class. And then the implementation of this, it reads it in from a file. Super simple stuff. Okay, so what you have to do for 90% of the assignment is just implement this function, okay? And so this is the compute function. It gets called in a number of different places in the environment. Someone in the chat asked, why do I use size t instead of unsigned int? Because size t is guaranteed to be the size needed to store an integer on your system, okay? If you use unsigned int, it's possible that you are on a 64-bit machine and it has 32 bits. And anyway, for anything addressing, I just use size t. That's something that I've always used. And I find it to work pretty well. So size t is just an unsigned int of the size. It has as many bits as your system is. So if you have a 32-bit addressable memory space, it'll be 32 bits. If you have 64 bits, it'll be 64 bits. Ooh, excuse me. So it's my go-to unsigned int. All right, so you have to compute this compute function. You get passed in the environment, you get passed in the spacing. That is the number of pixels in between grid cells. You get passed in the goal X and the goal Y. So I've done a little bit of this for you, okay? Let me make this a little bit bigger. So what I've done for you is the following. I've set the internal spacing variable to be the one that was passed in. And then I say, okay, I'm going to compute the width and the height of the vector field. The width and the height of the vector field are not in pixels, it's in the number of cells, okay? So the way we compute the width and the height, which is the number of cells, is we take the width of the environment, which is in pixels, and we divide it by the spacing, which is also in pixels, right? So if we have like a 3200 pixel wide environment and our spacing is 32, then we would have a 100 cell wide vector field. I also just record the goal X and the goal Y in case you want to use them somewhere else. Okay, and now I've given you sort of pseudocode that you can go through and implement things one by one. So whenever this function is called, you need to do the following things. First, compute the grid of blocked or unblocked cells. This is the M grid. If an environment rectangle overlaps a cell, you have to mark it as blocked. All right. So every time this function is called, essentially, you're going to have to reset the current grid variable, and it's going to be all zeros, and then you go through all the rectangles and you mark them all as 1. You have to compute the distance map using probably breadth first search, and then you have to compute the vector field of directions using the algorithm that we talked about last time. Use the techniques shown in the slides from the previous lecture to compute these values. You may create new functions and methods in vectorfield.h and vectorfield.cpp, but you cannot create any additional files for this assignment. And so what I've done is that's what you have to do, but I've also given you some sample code in order to show you how to set all this up. So here is how you set up a new grid. So remember, the grid is whether or not things are blocked or unblocked. So set the grid to be a new grid of all zeros. If the grid is not initialized, the GUI will crash due to vector out of bounds errors. So we set the m_grid variable to be a new grid holding integers, and it's going to have the width and height of the vector field, and it's going to be initialized to all zeros. Okay, so that's how you set up the grid. Next, we're going to set up the distance map, and the distance map is going to be initialized to a new grid of all -1. If this grid is not initialized, the GUI will crash. Okay, so if you don't initialize all of the grids, that something will crash for sure. So the distance map grid is going to be a grid of integers, and that's going to have this width and this height, and it will be initialized to all -1s. Now, the directions will be a new blank grid of, well, it will be a new grid of empty direction vectors. So what do I mean by this? Well, so the directions is going to be a new grid, and it's going to store a vector of direction. So it's a grid, so it's a 2D array, right? And each of the cells in that array are going to store a vector of directions. So again, our syntax is the size, so the width and the height. And this is just the shortcut for the default constructor of a vector, okay? So this will place a new vector that has nothing in it into standard vector, into the directions grid. Now what we're going to do is we're going to manually set the value of grid cell 7, 5 in the X and Y direction as blocked, which will show up as red in the GUI. So if I go back here, if I run this, you can see that 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5. This is set as blocked, and so the user interface will see it's a 1, and it will draw it as red. Okay, so that's what this does, but that has been manually set. It has nothing to do with the rectangles. Next, what I've shown you how to do is here's how we get the directions. So I have set up, So I've set up a reference to the directions vector for a particular cell, and then I've added 2 legal directions to that vector. So here, for example, I've taken the directions vector, I've pushed back, so that adds to the end of the vector a new direction which has 1, 0. So this is go right, and because it's 1 in the x direction, which is go right. And then I've added another vector which is go down. Okay, so if I toggle the display of the vector field, then what you can see at this cell, we go right or we go down. Now, obviously, again, this is just hard-coded, has nothing to do with the actual calculation. I've just included it there so that you know how to actually use the API that I've given you. And then finally, something that you're going to have to do for sure is actually go through all of the rectangles in the environment. So if you, for example, want to know like top left X of the rectangle, then this is rect.x. Okay, really, really simple how to actually use this API. The rest of the code here is some helper functions that I've given you in the vector field so that you don't have to write this tedious stuff yourself. So for example, you can tell whether or not something, you pass in a cell X and Y location and it'll tell you if it's the goal cell. It just checks whether or not it's a goal. I have another thing here, which is valid cell. So what is valid cell means is that is it within the bounds of the vector field, right? So is the XY location, are X and Y both greater than or equal to 0, and are they both less than the height? Is valid pixel. I have messed that up. That is not correct. And I don't think you actually need that for anything. So I'm actually gonna remove is valid pixel. We don't need that. That was something I used in my code that you probably don't need. You can add it back if you want. So is valid cell is whether or not the cell is in the vector field. Get grid. This is going to, you pass in an X and a Y, and it's going to return the grid value for the blocked grid at that location. Get distance is going to return the integer, which is the distance at a particular location. And the last 2 functions are the get num directions. Okay, so that's the number of direction vectors stored at a particular location in the vector field. So if there's 2 directions you can go, that would return 2. If there's none, it will return 0. And what it does by default is it just returns the directions.getXY.size. So that's the size of the vector at that cell. And the get direction function is going to return the indexed direction that's stored in that vector. Okay, so that's also pretty easy to understand. I've just put them all there for you, and these are used by the user interface in order to draw things. Okay, so the is valid cell, get grid, get distance, get num directions, and get direction are used by the user interface to do that. Someone asked, if you're in a corner, will it return 2 directions? Not necessarily. It will return to 1 direction if you're on the same row or column, right? So we can show that. Let's fire up the solution code. So if I'm over here and I show the vector, then yes, the corner will have 2 directions, right? But if I'm on the same row or column, then you wouldn't go down to get here, right? And you wouldn't go right to get here. So answers that question. And that's basically all there is to the vector field class, okay? Is that's the stuff that you have to write to get a 90% on the assignment. So just let me take a little bit of a drink here. Okay. Now, the last bit of the assignment is going to require a little bit more involved stuff, okay? So if I go over to main, now we're going to step through how all the code for the assignment actually works. So if you are only interested in getting 90 in the assignment, you can stop here. Okay. If you're interested in getting 100, then keep going. So very similar to the last assignment, the assignment has this GUI, which takes in a config file, and then we run it. So that's how the assignment is done. So let's go over to the user interface and see how this works. Now, I've put a ton of stuff. This assignment took a crazy amount of time to actually make. There's lots of stuff in this user interface, okay? Most of it has to do with things like computing where I've clicked to drag the rectangles and resize stuff, and whether or not to show the grid lines or show the help. Like all that stuff, which rectangle do I have currently selected? I got offsets, and all of that stuff is stuff you don't need to worry about, okay? The stuff you might need to worry about is up here, pretty much. So here is the environment data. That's the environment I've set up. Here's the vector field object and the window that we want to draw to. These things are the things that you are really interested in when you are going to modify the user interface in order to draw your particles or your entities or whatever. All right. So what happens inside the run function of the user interface? Well, two things are going to happen. It's just going to say, okay, while the game is still running, I do the user input. I do the user input. And so that just handles my keystrokes and my mouse, and then I render, okay? So let's say you actually want to do the last 10% of the assignment. What I recommend is doing something like the following. So inside here, inside the user interface header file, you could do something like void handle entities, okay? Or maybe this will be update entities. So you've created this function. Now you go back here and you have update entities. And in here, you would update your entities and their positions based on the vector field pathfinding. So what you could do in here is you could create a bunch of entities, randomly place them in the environment, store their positions, and then in order to say, okay, where do I need to go to get to the goal, you would look up in the vector field, which direction do I head in, and you would move the entity toward that direction, okay? It doesn't need to be as fluid or as nice looking as mine does, but that's essentially what you would have to do. And then, of course, up here, what you would do is you would have update user entities would have to, or update your entities that would have to be called every frame along with the user input and the rendering, okay? So you create your function. I mean, you could also put it in here, but it's nice to have it all in one place in a function. Any variables that you want to create, you would just add them, right? So if you have a standard vector of maybe you create a particle class or something like that, you could have a standard vector particle here that you update. That's completely fine as long as you don't make any additional files. The one other thing that you would have to do is that somewhere down in the rendering, okay, you have to draw your particles, okay? So what I recommend, now the rendering function is kind of complex, but it's also really, really intuitive. I'll go over it in a minute. But what I would do is down at the bottom of the rendering function, because things are drawn in order, so if you draw something and then something else gets drawn on top of it, you won't see your thing. So what I would do here is say, draw all of your entities. So for example, if I have like standard vector of my particle class, right? So if this is my particles that I have on the map, then I could say for auto P in particles, maybe I have a SF rectangle shape, rect, and then I would like rect.set position, and then let's like particle.get position, and then I could say rect.set fill color, and that might be SF color, like let's want a red color, so we'll do this, and then I would say mwindow.draw rect. Okay, so that's what you would do in the rendering function. It's very, very basic SFML stuff. You don't need to learn the whole library. You just take the position, the size of your particles, and you draw them all. And you do it down here at the bottom of the rendering function. Okay, so let's look over the whole user interface really quick, just to see how it works. Well, it's not going to take a long time. Essentially, there's this user input function that gets called first, okay? So yeah. So if I'm up here, if you've got your update entities function, that's fine. You'll call that. Then it calls user input. And this is a big long thing that just handles like, okay, if the keyboard, if this was pressed, do this thing. So for example, if you wanted to toggle on or off your particles, you could do something like this, where you say, I'm going to put in a new key, which is P. And then if I have some variable, which is like m show particles equals not m show particles. And what this does is that if I have a Boolean for displaying or computing my particles, then whenever I hit the P key, it will toggle that between true and false. Okay, so that's how you would add a key to do something if you want. I have all this code here, which absolutely doesn't matter. And now there's a ton of logic in here, and it's kind of complex because I've done a drag and drop system and a resize system absolutely from scratch, okay? So this is computing all of those things, so you can just ignore all of that. It's like 100 lines of code just to move rectangles around. I've got some code here for drawing lines. I've got some code here for drawing rectangles that uses a vertex array, which I'm not going to get into. It's just essentially an optimized way of drawing stuff. And then the actual rendering, it clears the window, clears the line strip, clears the quads. It sets up some shapes and some colors. It draws all the tiles on the map, whether or not it's blocked or not. It's going to draw, what's this? It's going to draw the text for the distance, right? So if we look here and I have the distance map turned on, it's got to draw this text. Then it draws the vectors for the directions, and then it draws the grid lines, and then it draws all the rectangles. Okay, so that's the order it does it in. So if I just want to go over that again. So first it's going to reset the background, then it's going to draw the red cells for the blocked things, then it's going to draw the text for the distance map, then it's going to draw the lines for the vector field, and then it's going to draw the rectangles on top of all that. And if you have particles, then it's going to draw the particles in there somewhere. I've chosen to draw my particles on the bottom layer so that it doesn't overlap anything else. And that, I think, oh, and then it draws the timers in the bottom left, right? So you can see those timers if you want. And then the help screen, what it does for the help screen is that you create a, if we look here, if I press H, it kind of dims the background, but it's still active to draw this stuff. So what that does is it just takes a semi-transparent black rectangle, the size of the whole user interface, draws that, and then draws the text on top of it if the help screen should be displayed. And that's it. So if you want to get that last 10%, you're going to have to get a little bit dirty with the user interface, but I think that's where things start to get a little bit fun. And then remember that if you want 5% bonus marks and you've got a lot of time to kill, you can also add in some steering behavior to your code. That, the last thing I'll talk about is just this timer. So I want to show you how the timing test is done. So what I do when you hit the T key to run the timing test, it actually runs this function. It prints out, okay, we're going to run the timing test. I start a new timer. So the timer class that I made, when you create the object, it starts the timer. Well, all it does is record the current time. Then what happens is I'm going to, for each cell in the field, if it's a valid location, right? So if it's an unblocked cell, I'm going to increase the total count, and I'm going to call the compute function on my field for that cell. So for every cell on the map, it's going to call field.compute. Then I'm going to count the elapsed time it took to run all of those and then display that to the screen. Okay, so the timer code is really easy to use. You just set up a new timer, and then you say t.elapsed whenever you want to know how much time has elapsed. So if you want to time your code or very specific things, you can absolutely use the built-in timing class to do that. Oh yeah, so the last thing I wanted to mention is that the way the user interface calls the vector field compute function is done through this recompute vector field function. So many things can trigger the recompute vector field being called. One of those things is the dragging of a rectangle. So whenever a rectangle moves, recompute vector field is called. Whenever a rectangle is resized, recompute vector field is called. Whenever the goal moves to a new cell, the recompute vector field is called. And whenever I resize the vector field grid, the recompute vector field is called. Okay, so what that does is it sets up the goal position based on the mouse position. It starts a new timer. It calls the vector field compute function, and then it says, okay, how much time has elapsed, and then I can put that to the screen so you can see how fast your stuff is running. Okay, that is about it. Let's go back over to the schedule and see. So you have 16 days to do that. So the day before midterm break is when that one is due. Okay, so that should be enough time to do that. But this assignment isn't necessarily that conceptually difficult, but there is definitely more sort of grunt programming work that you just have to get through in order to get it done. Okay, all of you did 3200, or you should have, because it's a prereq. And so you've all done like the flood fill breadth first search that you did on assignment 2. This is going to be extremely similar to that. Okay, you're just doing it in C++ instead of JavaScript. So next class, we're going to go over, we've talked about grid representations so far. The next lecture is going to be sort of space representations 2, where we're going to talk about more, not necessarily complex, but different space representations, such as graphs, arbitrary navigation meshes, and triangulations and stuff like that. Then we'll talk about a little bit of search and planning, but a lot of 3200 was on search and planning, so there's not going to be a lot of that in this course. And then we're going to talk about an intro to procedural content generation. We're going to talk about how, like, the procedural content generation that we'll need for assignment 3, which is completely on PCG. Actually, we're going to make essentially a 2-dimensional version of No Man's Sky for assignment 3, so that's pretty cool. And then we'll be giving out assignment 3 right before the midterm break. And so that's it. I don't see any more questions in the chat, so I'll end it there, and I'll see you in the next lecture.